To this point, we've been using cryptography to scramble messages to ensure secrecy. But there's another use for cryptography, and that's ensuring message integrity. The difference between secrecy and integrity is with secrecy, nobody can read your message. But that doesn't mean they can't change your message. So if you have the ciphertext and somebody intercepts it and modifies it, that ciphertext will decrypt into some plaintext that has been modified. And there are some cryptographic systems where it's pretty easy to modify it in a really malicious way. Think about a bank account transfer where you know a certain part of the message is a dollar amount. You can modify that and it'll change to be a different dollar amount. Now, you might not know exactly what dollar amount you've put in, but what you do know is you've changed the dollar amount, and unless something else is done, the receiver won't know that it's been changed. Also, sometimes you don't actually care about secrecy. What you care about is integrity. For example, if you're ensuring that a software image is downloaded to a system without being changed, it might not matter what the binary code image is, but it might matter a lot to make sure no one's changed it. So for those kind of applications, you don't want secrecy, you want integrity, and that's what secure hashing and digital signatures do. With these approaches, cryptography is used to ensure integrity via creating a digest. Now, what's a digest? Well, a non-secure digest is a checksum or CRC used to ensure message integrity. The reason I say those are non-secure is it's very easy to computationally break and recreate or forge a CRC, even if the polynomial for the CRC is secret. So don't do that. CRCs are not secure. But it's the same idea. You take a large message, you create a pseudorandom, smaller version digest of the message as a way to say, all right, if this digest matches what you would expect from the big message, then no one's changed the message. So the catch is we want to do that in a secure way. There's a huge advantage to using this type of hashing or signature approach compared to encryption, and that is usually get a blanket export exemption because you're not trying to keep secrets, even though you're using strong cryptographic algorithms. We'll come back to that in another lecture. First, let's look at symmetric cryptography, which can create hashing functions. You take an input, you run a cryptographic hash function on it. Basically, you encrypt it, but instead of taking the full message as the output, you combine all the values of the output into a smaller digest. Maybe you just XOR them all together into a short version of the message. The same secret key is used to check validity, but instead of decrypting it, what you do is you receive the input, you receive a digest next to it, and the sender computes the digest across the input and sends the digest. The receiver gets the same input, the receiver computes the digest, and if the received digest matches the digest computed by the receiver, that means the message has not been altered. So if you know about checksums and CRCs, this is exactly the same idea. The only difference is that instead of using a checksum or CRC, we're using a symmetric, cryptographically secure function to generate our hash. Both the sender and receiver must have the same secret key, and that means the receiver can also forge a signature because they have the key. If you're worried about the receiver not being able to forge signatures, you switch to asymmetric cryptography and use a signing process. This is exactly the same idea, except the secret key is used to create the digest and the public key is used to check validity. With signing, the receiver cannot forge a signature, but because it's asymmetric public key cryptography, it's going to be more expensive. If you wanted to implement secure hashing or signing, you could use, for example, AES for the symmetric cryptography and some public key algorithm for the asymmetric cryptography.